Okay, so can everyone hear me? Yes. Perfect. So thank you for the opportunity to be here to give you this talk. As you can see from the title, I'm going to talk about resonant cavities for gravitational waves, which I think obviously is going to fit the bill of this workshop, since resonant cavities, we all know, operate in sort of the gigahertz regime. But I will talk about how one can extend their sensitivity to lower frequencies, maybe as far down as a kilohertz. And the bulk of what I'm going to say is based on these two papers down here below. So indeed, I will talk not only about standard resonant cavities searching for gravitational waves, but also something that will then be built on in the following talk. So before we get into it, seeing as how this is the first talk of the workshop, I thought we would start with an exercise. So a little warm-up. This is my theorist's view of an experimentalist's ruler. And I'm going to ask the question, when is this ruler rigid? Because ultimately, the answer to this question will inform how we should search for gravitational waves across different frequency ranges. So let's consider the first simple situation where an incoming gravitational wave, depicted here by these double wavy red lines, is a very, very long wavelength compared with my ruler. So as you can sort of intuit, what is going to happen here is that the whole object is just sort of going to move back and forth. There's going to be bulk motion of the entire object because it's not able to respond resonantly to this incoming gravitational wave. And you should think of the LIGO mirror as being an example of this situation, right? You know that the LIGO mirror is relatively small. The gravitational wave is a very long wavelength. The mirror moves back and forth, and we're able to detect those small movements. If, on the other hand, you have an incoming gravitational wave whose wavelength is more or less matched, so here there's two wavelengths to my ruler, but you can imagine some number, integer number or semi-integer number of wavelengths to my ruler, then you actually resolve the structure of the ruler. And by structure, I mean the resonances of the ruler. So this could be mechanical resonances if this is truly a ruler. It could be electromagnetic resonances if the ruler is, for example, cavity modes in an otherwise empty cavity. So as an example, you can think of the Weber bar, right? The quintessential gravitational wave search from 60 years ago as being an example of this setup. Now, on the other hand, if we have a very short wavelength gravitational wave, so here I've tried to put as many of these little wiggles as I can possibly put without losing the sense of the slide, you can imagine that what's going to happen is that the ruler basically becomes fully flexible. And if you had the infinite number of wavelengths per ruler limit, even shorter than, say, the intermolecular spacing or something like this, you can imagine that the ruler basically breaks down into a bunch of free-falling particles. And so this should already inform your intuition as to what's going to behave in this particular way. So at the level of equations, I'm going to write this sort of standard equation of motion where I've got my Newtonian force in the proper detector frame due to the gravitational wave h acting on some ruler with length s. And I'm going to ask what happens in these various limits. So clearly, if I'm in the long wavelength limit, then the dt squared on the left-hand side is going to be negligible compared to the k squared, which is some intrinsic quality of the object. And so I can just straightforwardly solve for the displacement, and I'm going to find that it looks like it goes like omega g times some length scale squared, because you can imagine that this k is somehow associated to the length scale, 1 over L. So this looks very much like your usual intuition for calculations in the proper detector frame. If, on the other hand, I am in the very, very short wavelength limit, the k is sort of irrelevant. Everything on both sides is dominated by the dt squared, and I can solve, and I just find that s goes like h times s. And so you will remember that this looks a lot like calculations that you would do in the transverse traceless gauge, or TT frame. Of course, there was the third situation that I mentioned in the middle, but this requires knowledge of the detector, because I haven't written all of the terms that I could have written on the left-hand side of this equation here. Now, those of you who are awake will notice that the first line does not look like what I said it should look like, namely the LIGO mirrors, right? The LIGO mirrors move like the TT gauge, not like this omega g squared L squared. And the reason is that you shouldn't be including this middle term for the LIGO mirror, because you're not trying to resolve structure of the mirror. You're actually trying to resolve structure of the Fabry-Perot cavity. Okay, so having done this warm-up, let's consider the first example, where light is going to be my ruler. So now don't think of a physical ruler. Instead, think of electromagnetic waves in a cavity. So in order to compute what's going to happen in this situation, let's return to really basic stuff. So let's write down the electromagnetic action, taking into account possible curvature. So I've got all sorts of factors of G up here. I've written the current term there just for completeness, but I'm really only going to be interested in the FF term. So already you can see that when I do my decomposition into flat space plus some perturbation on top of it, h mu nu, that this interaction with 2 powers of G contracted into FF is going to give me a leading order term in my Lagrangian that goes like h times f squared. So for those of you in the room who no doubt there are many are familiar with axion physics, you're starting to think, okay, I know this game. So at the level of the equations of motion, you can go and write down what happens to df, and you find that it goes like minus d of h times f, which in a little bit more detail, you can write things as having an effective current where the gravitational wave, which has either spatial or temporal variations of h or of f, act as an effective current that in the presence of another field, some background field, so f is non-zero, will lead to a new field being produced in some region of space, and in this case, a resonant cavity. Okay, so to go into a little bit more detail than that, one thing that one has to do is compute something like this eta parameter, which is what I would call an overlap factor, which is basically saying if I have some spatial part of my J effective, so J effective is written in that little blue box up there, and I have some cavity mode that I can do some decomposition of cavity modes into a set of orthonormal modes. If this overlap factor is non-zero in the volume of the cavity, then I will be able to excite the mode. So the question is, of course, which modes are excited, how much, and can we actually look for those excitations? So indeed, again, those of you who are familiar with axion physics should be thinking, hey, I've seen this eta parameter before. This is something that ADMX, for example, calculates, or Haystack, or any number of these axion cavity experiments. And indeed, I could have written rather than writing the effective current the way I've done it up there, I could have given you a Feynman diagram, which is the one corresponding to the Gertzenstein effect, with this effective current that looks like the derivative of h times f. You would have said, hey, that looks a lot like the Primakov effect diagram that I would normally write for axion physics, where I have an effective current that goes like my axion coupling times the derivative A times F. And so for those of you who are familiar with the sensitivity of axion haloscopes to axion dark matter, you should already be able to open up your favorite calculator and estimate the sensitivity that I'm going to show you in about 5 slides' time. By the way, this is not something that was new to our work. This has obviously been noticed a long time ago, and I think the first paper that really quantified the analogies between axion conversion and gravitational wave conversion in background magnetic fields was this paper by Rafelt and Stodolsky about 35 years ago. So we have all of the machinery that we need in order to compute what we think the signal is, but before we go away and compute, we should think about what is the appropriate reference frame to work in. So of course, again, those of you who are awake are going to say, hang on a minute, I'm going to turn on my microphone. Frame shouldn't matter, right? Because this is gravity. One of the whole points of general relativity is frame invariance. So I shouldn't care about which frame I actually compute in. I should get the same result either way. The answer is, of course, yes, you're completely correct. However, there are frames that are easier to work in than others. And I'm going to argue that the proper detector frame, in which my magnetic field that I'm applying across my cavity is static, or at least approximately static, is the appropriate reference frame to work in, because then I know what my detector is doing, and all I need to worry about is what is my gravitational wave doing. So I'm going to work in the local inertial frame, where my nice 19th century physics holds, at least to a very good approximation. And so I would recall that if I work in that basis, so in this local inertial frame or the proper detector frame, in which my magnet is static and my magnetic field is therefore static, this is not the same as if I were to work in TT gauge, where I would need to take my otherwise static in the proper detector frame magnetic field, transform it to the frame of the gravitational wave, and I would find that it was jiggling around. So, which frame is the right one to use? Well, I would argue the proper detector frame. However, there is a complication. So if I'm going to work in the proper detector frame, and I think about what the metric looks like in the usual proper detector frame as given, for example, by my colleague Michele's textbook, you would see that you've got a very nice compact expression, but there's a very sort of suspicious-looking sim equals at the beginning of that line. And the reason why that's a sim equal is because this is actually the long wavelength approximation. So this is not the appropriate thing to do when I'm using an experiment with a resonant cavity with a static background magnetic field. Because, of course, my signal frequency has to be equal to my gravitational wave frequency for the signal to be resonant. And those of you who remember your Jackson will recall that omega signal is of order 1 over the length of the cavity. So clearly, I'm not in the omega g r cavity, much less than 1 approximation. So this has a clear sort of biohazard warning attached to it. And we recognize that the long wavelength limit is not valid in this situation. So what to do? Well, the answer, because GR is obviously a very old subject, was in the literature. It just needed to be massaged into a form that didn't look like this and looked like something a little bit more tractable. So the key sort of note to take was that if I just say that my gravitational wave is a superposition of plane waves traveling in a single direction, then any spatial derivative acting on Riemann, so here the notation is that these commas are derivatives of Riemann with respect to the indexed K1 or Kr or whatever, then I can just resum all of these expressions into something rather much more compact. So now I have, for a single gravitational wave propagating in the z direction in this situation with a frequency omega g, I can write down the metric. If I have a stochastic wave, I can just sum a bunch of different waves with different directions and different frequencies. If I have some wave that has a bunch of different directions, again, I can just do a sum. So now we have not only the machinery on the cavity side, but also the machinery on the gravitational wave side to be able to do the calculation correctly in the proper detector frame for the sensitivity of a haloscope to gravitational waves. So you will recall that the important parameter that I said earlier was this eta, which asked how much does my effective gravitational wave current overlap with an electric field mode of my cavity. And the answer is, fortunately for those of you who are running axion haloscopes, that axion haloscopes looking in the TM010 mode, or in some cases maybe some TM020, but in any case it doesn't really matter, the TM010 mode does have sensitivity to a gravitational wave as long as it's not coming straight up the bore of the cavity. Right? So this angle beta is the angle of the gravitational wave with respect to the cylindrical axis of the cavity. Since most of these axion haloscope cavities are indeed cylinders, you will see that if it's coming in straight up or straight down, the sensitivity is 0. But as long as it's any other angle, there is going to be sensitivity in an axion haloscope. However, I should say that TM modes are not optimal, and you can intuit this just from the fact that the gravitational wave is spin 2. This cavity with a static background magnetic field is not spin 2, and so I should try to couple to a spin 2 mode of the cavity. Yes?
Can you quickly say what a TM mode is?
Oh, sorry, yes, transverse magnetic mode. So this means that there is no magnetic field in the z direction, only in the transverse direction.
Where z is defined as the symmetry axis of the cavity always.
Okay, exactly.
Thanks.
Thanks. So just to flash what the possible sensitivity is of existing axion haloscopes, as well as a planned haloscope at FNAL's SQMS, you can see that the strain sensitivity is of the order of somewhere between 10 to the minus 22 to 10 to the minus 20 for different experiments. assuming a coherent gravitational wave, for which the power deposited in the cavity is given by that expression there. Now, I'm assuming here that the coherence time of the gravitational wave is longer than the ring-up time of the cavity, which is something like q over omega signal. So that should be borne in mind in the discussions that we have later this week when we're discussing how to compare sensitivities, how to discuss different sources, etc.
So what are typical values for the ring-up time?
So a cavity like, say, ADMX has a Q factor of about 10 to the 5. It's operating at about gigahertz, Q, yeah. So for stochastic gravitational waves, unfortunately, the sensitivity is nowhere near the BBN bound, as you can imagine just from looking at these expressions and just remembering that our sort of canonical aim, which is this capital omega g, scales like the little omega g cubed, and so this gets much worse the higher in frequency you go. So, given that I have 10 minutes left, I will try to speed up a little bit as we move on to Act 2, which is when matter is actually the ruler. So, we all remember the equation of motion for a test mass somewhere in space. We remember that the equation of motion is just this geodesic equation. We also recall that the effect of the gravitational waves is entirely encapsulated by the Christoffel symbol gamma. You'll also remember that I can work in the local inertial frame, and so that's what we're going to do again for the case of when matter is the ruler. So, as those of you who have looked into the subject a lot, you will remember that the effect of a gravitational wave in the local inertial frame can be written like a Newtonian force acting on an object. So when I go away and calculate what these Christoffel symbols actually are, it just looks like I'm exerting a force on an object, and it's therefore going to be accelerating, and that force is just given by this expression here, where I'm expressing the metric in the TT frame, even though I'm working in the proper detector frame. And you'll remember that I can do this because Riemann is invariant at order h. It only changes at order h squared when I change between different frames. Now, of course, we're in a simple setup because I can actually use the long wavelength approximation. And the reason for this is that the speed of sound in materials is typically much, much less than 1. Indeed, typically it's of order 10 to the minus 5. And so this is going to simplify my life enormously. I'm going to go back to my colleague Michele's textbook. I'm going to take his equation with the sim equals, ignore the fact that it's a sim equals, and take it as truth. So, again, why cavities? Now we can live in a situation where we have both mechanical and electromagnetic signals. And again, this is not something that was realized for the first time last year. This was something that was actually realized almost 50 years ago by these authors here, who suggested using a tunable electromagnetic detector for gravitational waves. And they noticed that the mechanical signal was dominant over the electromagnetic signal. This led to the MAGO prototype, of which a photo you can see here, and we're going to see lots of photos of basically the same cavity in Christian's talk in just a moment. So this was in the early 2000s, a collaboration between people here at CERN and in the INFN. And now there is an active attempt to revive this collaboration. And like I said, we're going to hear more about this in the next talk. I lost control. There we go. OK, so this is a picture of a theorist's view of MAGO 2.0. And you can see this very nice little cartoon where I'm showing that the mechanical and the electromagnetic signals are coexisting. So bear in mind that this is a theorist's view, and the cold, hard truths will come in the next talk. So the idea here is to take a cavity and load it in what I'm going to call the pump mode. So I'm going to dump a load of energy into an oscillating electromagnetic field at some frequency of order gigahertz. This cavity is going to be carefully designed so that I have another mode which does not have energy inside it, in principle. In practice, we'll see what happens, at some frequency omega 1, such that the difference between these two frequencies is much, much less than omega naught. These cavities are necessarily also going to have mechanical resonances, and like you will remember, I said that the speed of sound in materials is typically much less than 1. It's of order 10 to the minus 5, 10 to the minus 6. And so my typical mechanical resonant frequency is going to be of order 10 kilohertz. I'm going to assume that I have a gravitational wave that is coming in with some frequency omega g, which is maybe not so different from 10 kilohertz. And in this situation, I can have two signals. One is if my omega 1 and omega 0 are fortunately chosen such that the difference matches the frequency of the gravitational wave. And in this case, the gravitational wave is going to get resonantly enhanced in terms of its effect in exciting the signal mode of my cavity. If, on the other hand, I'm unlucky and my gravitational wave frequency is not the same as the splitting between omega 1 and omega 0, and here I'm showing it as being greater because this is a simpler situation to consider, I will still have power in the cavity. It will just be suppressed by the response of the cavity mode to that off-resonance signal. So how does this work in practice? How do I engineer a situation where I have all of these different frequencies playing around that I can then look for a signal in this cavity? So the answer is the following. You take a single spherical cavity. You have some resonant frequency associated to it, which is of order gigahertz. And you basically play the coupled pendulum game. You couple it to the other pendulum, namely the other cavity, through some coupling with some radius a. So I should have said that the first cavity had a radius r. These two cavities are now going to be identical and also have radius r. And this splits any single mode in the first cavity that I had into two modes, the symmetric and the antisymmetric combination, exactly the same way as what happens when you combine two pendula together. And the splitting of the two frequencies basically goes like the radius of this little connector here, A, over the radius of the cavity cubed. And that's in a paper by Beta from 1941. So if I have some incoming gravitational wave, it hits the symmetric mode and it excites energy up into the antisymmetric mode. And we'll try to read out the power deposited into the antisymmetric mode. Of course, that's a theorist view. The experimentalist's view is going to be a little bit more complicated than that. So in terms of the parametrics of the two signals, remember I said that these two signals coexisted. In the case of the electromagnetic signal, remember photons are the ruler here, and we're in the long wavelength limit. And so I recover exactly what I expect, which is that the signal electric field is suppressed like omega GL squared. Right? Remember the first couple of slides. If my ruler is a different wavelength, then here I'm going to recover this suppression. On the other hand, the mechanical signal goes like the minimum of either omega times L over CS, because remember that CS is much, much less than 1, or 1. And so what this means is that my mechanical signal is actually enhanced in most of the parameter space by 1 over the speed of sound squared, which is therefore much, much greater than 1. And so while these two signals do coexist, in this case, where I'm in the limit where the ruler that is given to me by the photons is sort of rather rigid, the fact that the other ruler is much less rigid means that my mechanical signal rules, if you'll forgive the pun. So in terms of the expected sensitivity, and again, I'm showing only one of the plots of the sensitivity. We're going to have a discussion about how to compare sensitivities later on this week, so don't kill me yet. This is, in purple here, two different setups, or rather 3 different setups for what MAGO 2.0 could potentially do. So one at the top there is using microphonics, so mechanical vibration noise, that was measured by Fermilab to try and estimate what the sensitivity would be. And I'm scanning electromagnetic frequencies so that for any given omega g here, I'm assuming that omega 1 and omega 0, the signal frequency and the background frequency, are selected so that their difference is equal to omega g. I'm also taking one where I have just thermal microphonics. And so obviously that is much, much better. And then you'll see in dashed I have this line called non-scanning. And this is a broadband sensitivity. So if you remember the sort of schematic where I showed you that the gravitational wave could still excite a resonance far off resonance, that's what that setup is doing, where I've selected the splitting between the signal mode and the background mode to be of order the lowest lying mechanical resonance at about 10 kilohertz. So there are a few important noise sources which dominate at various different stages in this setup. So thermal noise, which is familiar to all of those of you who are familiar with axion haloscopes, lives at high frequencies up here. So in this part of the parameter space, I'm limited by thermal noise. There are, of course, many more noises associated to this proposed experiment due to the fact that we're loading the cavity with electromagnetic energy at a given frequency. And there are no delta functions in nature, and so that energy is actually going to be spread over a range of frequencies. And so that's what I'm calling loading and readout and oscillator noise here. So oscillator noise is the spread from the fact that I'm loading this cavity at a given frequency, but I'm not loading it perfectly. I'm loading it over a range of frequencies. And loading and readout noise up there is from the fact that not only am I loading it with a spread in frequencies, but I'm also not going to be able to perfectly couple to the mode that I wanted to excite. I am always going to accidentally couple a little bit to the mode that I didn't want to excite. And then vibrations. So vibrations are both a signal, but also a noise. So if someone is stomping around in the lab outside of this cavity, it's going to induce small vibrations in the walls. And you can see that unless I'm in the thermal limit, this is going to be a bit of a problem. So those live at the lower end of the frequency ranges shown here. So you might be wondering, hang on a minute, you're just describing to me a Weber bar. Why on earth would you use a loaded electromagnetic cavity with all these different noise sources as a Weber bar when you can just build a Weber bar and look for the gravitational wave that way? Well, the answer is in the following observation. So you will say, but I can just increase the mass of my Weber bar almost arbitrarily, not quite, but close enough, and I'm just going to get smaller and smaller thermal mechanical noise. And you would be correct. But you would have noticed that the broadband sensitivity that I showed you on the previous slide was rather good for this setup, and that the sensitivity when I was thermal noise limited was also very good for this setup. And the reason is that when you are thermal electromagnetic noise limited, which does happen in Weber bar experiments because they're coupled to LC resonators in order to be read out, the noise scales like 1 over Q, also like 1 over the stored energy. And Q is just much, much bigger in a superconducting RF cavity than it is in an LC resonator. The best Qs in LC resonators were achieved by, for example, Auriga. That's of order 10 to the 6. In SRF cavities, you regularly reach 10 to the 10 or higher. And so you can beat down that thermal electromagnetic noise, which you will remember from the previous slide dominated in quite a large range of frequencies. So just to show you what this means in practice, these are the signal and noise power spectral densities in MAGO 2.0. So in blue is the signal, green is the mechanical vibration noise, sort of pinkish color is the thermal electromagnetic noise, and there's also amplifier noise from outside the cavity when I try to read it out. So you will see that on the right-hand side of this plot, here, by the way, I'm assuming thermal vibrations, which is why it looks so good. The electromagnetic thermal noise dominates above a broader megahertz, and my square of the strain sensitivity is going to go like 1 over Q. In this little region here, where I'm dominated by mechanical noise, and my signal is still mostly flat, the signal power spectral density is going to scale more or less like so, like 1 over omega g to the 4. SFP, by the way, is the power spectral density of the force that's being applied to the walls. So in this case, it's thermal, but in a general case, it's going to be something that you would measure in the lab. If I do the non-scanning experiment, you see that indeed my signal gets suppressed when I'm above the resonance that I selected. Remember, in the non-scanning setup, I fix omega 1 minus omega naught, but I look anyway at omega 1 minus omega naught at some omega g, and you'll see that it's suppressed by the Lorentzian, but so are other noise sources, with the exception of amplifier noise, which I said was external to the cavity. And so as a result, when you're at high frequencies, amplifier noise dominates and the scaling goes like so. And when you're at low frequencies in this particular range, the mechanical noise is dominating once again, and so the scaling goes as before. Note, by the way, that in these plots I'm neglecting something that's called radiation damping, which is mixing from the two modes together. And this could be important in some frequency ranges, and I invite you to look at this paper by Robin Löwenberg and Gudi Mutgat-Pick for more information. So to summarize, I'm not going to summarize, instead I'm going to ask some questions. So the first question is one for everyone here. Are resonant cavities really the optimal thing to do in the radio band? Are there advances in readout that we can do to push these sensitivities in the top plot, for example, to the left? This is obviously something that is very interesting for people also looking for axions. It might also be interesting and relevant to people who want to do quantum computing with SRF cavities, so maybe there's something interesting to be discussed there. There is, of course, the possibility of not just having one cavity, but having a network of cavity, and there has been some work done in this direction to ask what is the sensitivity when you turn these cavities into a network, and I invite you to look at this paper. There's a further question of what is the optimization of a MAGO-style setup. So can one ever really reach this thermal vibration noise floor? If you want to reach it, how do you do that? And this is, I think, something that is the subject of study at DACY and Fermilab currently. And finally, another very important question, which ultimately indicates what we're all doing here, is what are the signals above a kilohertz that we might be sensitive to, given what these experimental parameters seem to be telling us. So with that, thank you very much, and please ask any questions you have.
Thank you very much.